All right, so picking up where we left off, the logarithm. Again, option number one for any of these problems. Again, option number one is to use that one-to-one property. So again, as we're looking to use the one-to-one property, the real question that we need to ask ourselves is, do we have the same base? Do we have logs of the same base? If we have logs of the same base, then we have a real shot at using the one-to-one property. But in order to pull that off, then the left side of the equal sign, the right side of the equal sign, they each have to have logs of the same base. So then again, with that realization or the realization that this is not always going to work out with the one-to-one property, what are we going to do if we only have a logarithm on one side, or if we, I suppose, technically have logs at different bases? What we need to do is isolate that logarithm. If there are two logs on one side, we're going to use our condensing properties in order to get that to a single log. Once we have gone as far as we could possibly go as a logarithm, once we run into a dead end, then we're going to change it back over to an exponential and solve from there. So, last thing I wanted to talk about here before we jump into a few examples is that we do have a way of checking graphically. We're going to do this a little bit more in class as we go here, but again, I really want to emphasize that we are checking these graphically. This is not a good approach when it comes to solving, initially or for the first time, but again, we can check to ensure that we're doing things properly. All that we need to do is essentially we graph the left side of the equal sign, we graph the right side of the equation, and we calculate their intersection. We see where those two functions are going to cross or intersect. So again, a little bit more to come on that in the near future. All right, so here we are with the exponential. So this is very similar to the one we practiced here initially. First, I'm noticing that t is my variable that is written at the exponential level. So it's way too early for me to determine whether or not we can use the one-to-one property. So I'm going to start by adding the 4 over, at which point we now have 2 times the quantity 3 raised to the 2t minus 5 is equal to 11 plus 4 is going to be 15. Now, as we've said previously, our goal is to isolate the exponential. So that means that this 2 that's out front has got to go. So I'm going to divide both sides by 2. And now we're in a position to where we can say that 3 raised to the 2t minus 5 is going to be equal to 15 halves, or we could go decimal 7.5. Now, I believe we're at that point to where we could most definitely answer the question of, can we set up and use the one-to-one property? So please understand what we're asking without, exactly coming right out and asking is, could we rewrite 7.5 as 3 to some power? And the answer there is no. That's not going to be one of our perfect powers. Now again, if instead of 7.5, if we had 9 or 27 or something like that, then again, that would have been a totally different story. But we are not going to be able to rewrite 7.5 as a logarithm. So for that reason, we're somewhat at a dead end in terms of exponentials. We cannot go any further with this exponentially. So instead, what we now can do is we can consider rewriting this as a logarithm. So as we rewrite as a logarithm, we're going to say that that's going to be log base 3 of 7.5. That's going to be equal to 2t minus 5. Now I know it looks like there's a lot more going on, but this log base 3 of 7.5, that's just a number. That is a value. Yes, we could calculate that decimal really at any time, but we want to try to at least attempt to find the exact and the precise answer. So I'm going to start by adding 5 on both sides. Again, understand what I'm trying to do is I'm trying to isolate it. I'm trying to get t all by itself. And we're frankly just using our algebra techniques to get there. So on my left side now we have log base 3 of 7.5. But I've added 5 to that to equal 2t. We're almost home. Right here, I want t isolated by itself, so I have to get rid of the 2. And for that reason, I'm going to divide both sides by 2. Now, on the right side, these 2's will divide out, and t is going to be equal to, if we needed the exact value, there it is. Looks like a mess, though, and under very seldom circumstances would you identify that your answer is log base 3 of 7.5 plus 5 all divided by 2. Instead, what we would do, most typically in that situation, we would calculate that decimal to 3 places. In this case, I'm getting approximately 3.417. As we take a look at the problem on the right, very similar, it's another exponential. I'm going to make the argument that this one's easier, not because e is involved, but because we have common bases, so I can use the one-to-one property. So my exponents, negative x squared and negative 3x minus 4, they're going to be set equal to each other. So my first move is to get all the x's to the same side. So I'm going to add the x squared over. So now we have the ability to say that 0 is equal to x squared minus 3x minus 4. And I can now factor. So this one does factor in the traditional sense. Multiplies to negative 4, adds to negative 3. We say that's positive 1, negative 4. So as we set our factors equal to 0, x plus 1 equals 0 means that x equals negative 1. X minus 4 equals 0. That tells us that x equals 4. But we came up with our solution that way. So once again, different ways of obtaining our solutions or our answers. Again, on the right over here, we were able to use the one-to-one property, so that problem likely felt easier or smoother. We're going to circle back to this one. Again, we're definitely going to talk about that more in class tomorrow, so I wanted to get into some logarithm problems here as well. So initially, this first example kind of looks like a mess, frankly. We can see that we've got log base 6 of 3x plus 14 minus log base 6 of 5. That's equal to log base 6 of 2x. So it looks messy because we have so many logs up there. The first bit of good news is that they're all log base 6. So again, we all have logs of common base, which means that we have a really good chance at setting up and using the one-to-one property. So what I need to do initially is I've got to get this left side condensed down to one single logarithm. So remember our condensing rules when we are subtracting is that I could turn a subtraction problem into a division problem. So I could rewrite this as log base 6 of 3x plus 14 divided by 5. That's now equal to log base 6 of 2x. So again, the one-to-one property is most definitely in effect here. We have log base 6 on both the left sides, so log base 6 of 3x plus 14 all over 5 is equal to log base 6 of 2x. Well, that just tells me that 3x plus 14 over 5 is going to be equivalent to 2x. Now, the way that we go about solving for x, frankly, we have options. Again, I could clear the fraction on the left by multiplying both sides times 5. Again, looking at something like this, we could absolutely do it this way. Another tactic that we could use that is relatively popular is that students will look at this and say, well, 2x is really over 1, and now I can cross multiply, so we get 5 times 2x. Either way, you're going to get 10x is equal to 3x plus 14. And once we're here, now it's a matter of solving using our algebra technique. So I would subtract 3x over, you get 7x on the left is equal to 14 on the right. Dividing both sides by 7 is going to allow us, or enable us to say that x is equal to 2. Now, the problem down here, I know that, yes, we did go through this one in 7th period. Let's pretend that you don't see the answers here just for a moment. So the difference with this problem, or again, what jumps out probably initially, is that we don't have as many logarithms. We're not all over the place in terms of, like the previous example where we had 3 different logarithms. Instead, we just have 1 logarithm. So here, as we set into this, it's probably a good indication that we're likely not going to be able to set up and use the one-to-one property. So instead, my focus now is to get that log base 4 all by itself. Meaning this 3 that's out front, it's got to go. So I'm going to divide both sides by 3. Now my left side, we've done it. We've isolated the logarithm. We have log base 4 of 6x is equal to 9 divided by 3 is just going to be 3. So if we are attempting to set up and use the one-to-one property, we know that we're at a dead end. If I were to try to go any further with logarithms, again, we are at a dead end. We are not going to be able to go any further with logarithms, but we now have the ability to go ahead and change over to exponential form. So my base is 4 raised to the 3rd power is going to be equivalent to 6x. We know that 4 cubed is 64. As soon as we have that 64 equals 6x, we know how to, again, it's just algebraically solving from here. I'm going to divide both sides by 6, so we've isolated the x is equal to the 64 over 6. Well, that's going to reduce, as we had behind the box there, it's going to reduce to 32 thirds, or 10 and 2/3. But as we said before, we usually, most commonly, are going to go with 3 decimal places. So if we were to stay consistent with that, we're talking 10.667. All right. So we did a couple of, in 5th period, we had a chance to do the group work. So just for some extra practice, let's go ahead and talk about some of this group work and what's going to happen. So again, not looking likely that we're going to be able to utilize the 1-to-1 property. So if I were to add the 3 over, that's going to give us 7 raised to the x minus 10 is equal to 65.1. And yeah, I think we can confirm that. I'm not going to be able to write 65.1 as 7 to some power. So instead, we're going to now transition over to logarithms. So we're going to go log base 7 of 65.1, and we'll say that that's equal to x minus 10. To isolate x, I'm going to add 10 to both sides, at which point now we can say the exact answer here. We're going to say log base 7 of 65.1 all plus 10. When we type that into the calculator, hopefully I have this written down. Looks like we're going to obtain 12.146. All right, similarly, if we were to take a look at this second example, very similar to the first one that we did, I'm noticing that we have 3 different logarithms up there, but the good news is that they're all log base 3. So on the left side, I have to condense. I'm noticing that we have an addition problem, so we're going to be able to condense an addition problem back to multiplication. So we'll be able to rewrite this as x times x plus 9, all of log base 3, and that's equal to log base 3 of 70. So as I clean this up, I can actually multiply and get a little bit further. We're going to call this log base 3 of, as I distribute, we'll call this x squared plus 9x, and that's equal to log base 3 of 70. So as we can conclude using the 1-to-1 property, we can conclude that x squared plus 9x is actually equal to 70. So now as I subtract the 70 back over, x squared plus 9x minus 70 is equal to 0. And yes, this is now a factoring problem. So we're considering factors of negative 70 that add to positive 9. So hopefully we're thinking positive 14, negative 5 should do the trick. So when I said x plus 14 equal to 0, x is then equal to negative 14. When I said x minus 5 equal to 0, now x is equal to 5. So we were able to obtain those answers as well. All right, so if you remember back to the very beginning of class, we said the type of problem that we were going to look into would be one of these investment problems. So again, the same problem, same setup. It says that you've deposited $1,000 into the account that pays 6.25% interest compounded continuously. How long will it take your money to double? So we already talked through the importance of understanding that if your principal is $1,000 and you're doubling, that your amount, your targeted amount, is going to be $2,000. So that's why we set up using the PERT formula the way that we did. But up until this point, or when we got to this point, we didn't really know how to finish and solve. So we are finding ourselves writing out the exponential form, and we're going as far as we can. But this is not a 1-to-1 situation. I'm not going to be able to rewrite 2 as e to some power. So this is where, again, we've got choices. We could do this the most traditional possible way, where I could rewrite the exponential as log base e of 2 is equal to 0.0625 t, and we could be successful. But we better not leave it as log base e, and instead we rewrite that as log. And that's true, we could do it that way, but our shortcut using our property is that anytime we have exponential base e, I can simply apply the natural log to the right side, so long as I apply the natural log to the left. That's going to give me the natural log of 2 is equal to, after this cancellation occurs, 0.0625 t, and we're almost there. Remember, the goal is to isolate t, so I could divide both sides by the 0.0625, like this. So my exact answer, natural log of 2 over 0.0625, but my actual decimal answer, we would say that to double that investment of $1,000, it's going to take approximately 11.1 years. So that leaves us with the one problem that we need. Oh, there it was. The one problem that we need to investigate a little bit further right here. I'm going to definitely talk about this one tomorrow in class. Again, I don't think I'm going to be able to knock this out in the last 25 seconds that this video is going to enable us to have. So again, focusing on the assignment that you can find on page 235, we're going to be turning that in tomorrow. You also received a worksheet today. That worksheet's not actually going to be due until Wednesday. So good luck with these. Come see me if you have any questions.